Hi everyone, welcome to another Common Lisp study group. I'm your host Ram Vedam with Atlanta Functional Programming. These past couple of weeks we've been going through a lot of different data structure libraries, and today we are going through yet another one that I felt was a very nice library of stateful data structure specifically compared to the two other libraries that we saw in FSET Sycamore that mainly focused on functional data structures. This library is called CL Containers. It is available on QuickLisp. Originally, we were also going to be discussing today Lisp Interface Library, but for those who are interested in the Lisp Interface Library, that is on the docket. I just need to go through it a little bit more in detail because there's quite a few concepts in there that I need to more or less kind of understand myself in order to better present some of the material. Now, those of you who are interested and want to jump ahead and look into some of it, I will provide some resources at the end of our conversation today, just so that if you're curious as to some of the design decisions and stuff, because the Lisp Interface Library has been around for quite a while, you can certainly go ahead and look at those resources, and it will hopefully provide better kind of like basis for a better discussion when we actually present it here at the Common Lisp study group. But putting that aside, all these data structures libraries that I've been showing you were kind of filling in the gaps that were more or less inside the Common Lisp library system as it stands today. So Common Lisp itself provides you many built-in data structures, but mainly three core ones. That is lists, arrays, which are more or less vectors if you're coming in from C++, or array lists from Java. They are contiguous-based data structures with random access iteration, as well as hash tables, which are available also inside Common Lisp as well. There are certain things related to but also there are other kinds of data structures that are specific to Lisp itself that are also around, like associative arrays, property lists, and so forth. But we're not going to focus on those a lot, just mainly because property arrays and associative lists are used, but very rarely nowadays, especially given the fact that associative lists, although very, very easy to make and very easy to iterate with a decent API, unfortunately, because of the fact that they're not very cache friendly, you might end up hitting some performance problems as you start using them in much larger code bases and much larger use cases where it's clear that the number of items inside of the list might overpower your caches. So there was a clear need for a lot of these different data structure libraries to be created, and there are many of them out there. The ones that we covered so far, FSET and Sycamore, are two quite popular, fairly complete libraries too, that you can use for your production code, and they both provide a fairly decent approach to actually providing more of a uniform API than what Common Lisp currently provides, because if you are familiar with our existing data structures, lists and vectors, which are both part of the sequences protocol and implement the sequences protocol, they more or less have a uniform API that you can switch between either a list or a vector depending upon the use case. But if you wanted to use, say, like an associative list or associative array, or a hash table against the same API, then you're kind of out of luck because those APIs don't deal with key value pairs very well. So FSET and Sycamore kind of address this with their own kind of APIs, and similarly CL Containers, which is the one that we'll be discussing today, has kind of taken that same approach too. It provides somewhat of a uniform API across all of its data structures. Now, the documentation is available on commonlisp.net, and as well as there's a couple of very nice diagrams that kind of show you, there's one that's somewhat irritating. It's a bit of a complicated class hierarchy, but he himself said that it's a crazy class hierarchy of all the classes that are available. But the second one, which is a diagram of the list of generators that allow you to lazily iterate through the data structures themselves, is somewhat useful. We may not be able to cover all of them today, but I'm just going to give you some highlights across some of the ones based on my experiences. I'm still going through this API because there are quite a few interesting data structures that are available in here, and I'm not entirely sure what their differences are with some of the built-in ones. Particularly, there is a flexible vector container as well as a vector container inside of this API that I'm honestly am not so sure what exactly the differences is with that and the dynamically sized array that you can make with MakeArray. So I'm still working through on some of that, but I'm going to give you some of my initial findings today, and if need be, we can, I can present another episode of this just so that I could finish off some of the other ones. Today, mainly, we're going to be focusing on the design decisions, some of the core things that this API kind of provides, and just highlight some of the interesting data structures that are available at your disposal if you want to use, so you don't have to, if you ended up needing any of these, you don't necessarily have to, reinvent the wheel. So CL containers is based on this idea that, again, we should have a set of powerful built-in data structures that are not available in Common Lisp right now, but also want to provide a standard interface so that you could switch between any single data structure. If you're writing your application, turn out that the adopting one ended up having some sort of like performance issues or some characteristics that you did not intend to have inside your program. The main things that these guys are all implemented off of, and this is something that should be aware, is they are all based off of this abstract container class that they provide. So if you ever wanted to write your own, user-defined data structure, you could just, in order to hook into the CL containers library, you could certainly, let's, just call this, dumb stack or something like that, because there's already built-in stack data structure that I will cover later on. You could simply go ahead and adopt this by going into, oh, my apologies, I forgot to load in the data CL containers library. You could just simply implement this as an abstract container, and this is going to allow you to hook into the basic API that they provided to as well. So as you go ahead and implement your data structure, you can also override those specific functions that are available to you. And these are things like collecting, counting, first item, last item. You can override the generator function to convert your data structure into something that can be evaluated on demand and iterated through on demand. There's different map functions available at your disposal to transform your data structures from one to another and so forth. So this abstract container class is available to you so that you can go ahead and implement your data structures and have them seamlessly integrate into the higher level API. Additionally, there is another top level class that deals specifically with first in, first out kind of semantics, and that is abstract queue. There's a couple of mix-ins related to that you may want to also check out, which brings me to another thing that I want to mention, and that is CL containers is heavily mix-in based. That is, there are a ton of mixins to provide different sorts of functionalities. So if you want associativity based on key valueness, you can use the associative container mixin or the bi-associative container mixin. There's mixins associated with determining if your container is a node-based container versus a contiguous-based data structure, and as well as determining whether or not internally the implementations is like an array or a hash table as well. A lot of these mixins are more or less hints to the higher level protocols, and they have already built fairly efficient algorithms on top of them for some of the APIs. So you could just simply, hook those in through adding them as part of your inheritance list, and you'll get that functionality for free, which I thought was pretty nice. So, what is actually provided by this library as is? That is, what data structures are available to you without you having to go and write your own with the mixin architecture that's available. Well, there are a couple of well-known ones. I will say that in order to make it easier to use the same API across existing Lisp data structures, they've implemented a couple of wrapper containers, I hate to say it, to allow you to access these guys. So the first example is, because I brought up associative lists earlier, is you can actually go ahead and make an associative list by going into, if I remember correctly, single containers make container. So this is something that I want to also kind of bring up, which is the top level constructor for all basic containers is this make container class. It's not make instance. My understanding is they do some additional, this is I think just a wrapper around make instance, but it provides some additional functionality. But it's, hold on 1 second, let me just double check my notes here. Did I write this wrong? Where is it? Well, I wrote about make generator, but I didn't write make container. Okay, so if we go and actually just look into this signature, this is probably the easiest way to show this to you. You can see that it's just basically a generic function that you can literally override for your own container classes. This, again, is around what I was saying before, this uniform API. They want the construction to be uniform. They want the ability to use the various containers so you could switch and mix and match. Try to switch and try and look at through the profiling, whether or not different data structures can adopt different behaviors, so you could find the best one for your use case. This uniform API really allows you to go ahead and do this. And you can see that this generic function has already been overridden for the majority of the basic data structures that we'll be talking about today. So make container obviously is like make instance. You have to specify the class that you're creating as well. And let's see, a list container is what I'm going to go for. Oh, sorry. There we go. Yeah. And as you can see in the signature here, which I'm going to go ahead and see if I can get myself into the mini buffer, but it looks like I can't. How did I do that last time? Increase the mini buffer size. 1 second. Okay. So I hope folks can actually see this, but unfortunately, right now I can't seem to recall how to increase the mini buffer uh, size right now. But the last argument is that we can actually go ahead and instantiate this guy with the rest of the arguments that you want. So in this case, since we're this associative list, which is a set of key value pairs, let's say, A1, let's say E2, C3. Okay, so the string is our key, and our value is going to be a number. All right. So if we go ahead and construct this, argument is not a symbol. Oh, my apologies. I did this wrong. I actually passed in a list rather than just a set, because these are rest arguments, right? A1 is equal function call. Oh, sorry. I gotta make sure I do this. Okay, let's see if this works here. Let me make this wrong. This worked before. Let me see something here. Let me see if I could just do this. So I thought I did one of these things. Let's get rid of an associative list. Let's see. Argument is not a symbol A. Let me try this. Interesting. This looks like it worked. Let's see what this is. Those are symbols. Nil, nil, nil. You see, this is wrong, but it did not insert the item the way I expected it to, which means it just created an empty list. This is interesting. I have to go and look this into. This should have worked before the way I had it, but it looks like it was incorrect. So let me go ahead and use the basic uniform API just so that I don't confuse folks. So when you first create this make container, you'll get an empty container, as you saw here earlier. This guy basically has contents nil, has an initial element or not, which should have been true earlier, but it didn't for some reason work the way I expected it to. So that's a little bit of a difference in understanding. And you can see there's also three other things that are there. There's a built-in test here that's very important to keep in mind, because this is part of the difference between CL containers and a lot of the built-in data structures. The built-in data structures, a majority of them, whether it's associative lists, arrays, or hash tables, the default test for filtering in a lot of the sequence functions is actually EQL, which is equal by identity, not actually equal, which is based on if you have an equality operator for your two types that are inside of it. So whether or not it's string equal in the case of string, character equal, or what have you. This is something to be aware of. I don't believe you can actually change this right now, at least from my initial findings in the library, although I'm looking into this, just because obviously in the case of wanting to be able to use things, say, with pointers, in the case of in Common Lisp, not pointers, essentially const cells, this might be more efficient if you can actually end up using equal by identity, EQL, instead of equal. But for now, this is something to be aware of. Folks who might be familiar with this library a little bit more than me and are aware of, for example, how one might use this and change the test function, please let me know. I haven't had a chance to actually go and look into some of the details of this just yet, because I've been working through their essentially the Common Lisp as if quick docs documentation on this, which has some very minimal understandings on some of this. Some of these functions and what they're working through. They're basically ripped out of the actual comments inside of the documentation inside of the code. So we have an associated list. What can we do with this? So we can actually add stuff, we can remove stuff, and we can filter things. I'm just going to first go through inserting a new item into the container. And to do that, you have essentially, sorry, let me do it here, CL containers, insert item, you specify the container. In this case, since A-list container is of type I'm using the wrong insert because it is a associative container, it's not a non-associative container, which means I should be using, let's see here. Let's see, maybe add initial contents is what I need to use. Add initial. For some reason, some of these things that are inside their documentation, I don't, again, encourage you to use the colon just because you're essentially looking at implementation specific things, but there are things in their API docs that are hidden still, which has been frustrating me when I've been playing with this. This is one gripe I have about this library, just because I'm always finding something something really, really interesting about it. Let's see now. How do I create an associated? This was a list. So this is the right syntax of this. Let's see. It's a and go into the container. There we go. That's the correct one, syntax. All right. So when you're using add initial contents, you pass in an associative list, which for most of you are aware, the associative list, basically the first value, every other value is the key, and the key and values are key value, key value, key value. So in here, what you have to do is pass in a list of an associative list, and then what CL containers does is it internally creates essentially a list of dotted pairs for you. And you can see here that, again, even though there are contents here, initial element is still unbound. Initial element function is still nil, right? And the test function has not changed. Okay. So what's important about this is that there's no initial element here, right? Although there is contents. So what this does is this kind of makes things a little bit screwy, and I'm still trying to wrap my head around why this is the case, to be honest. But if you end up calling, they have an a predicate function called has, what was it? Has initial element p. What was that? What was it? Initial element p. There's an accessor that allows you to actually check to see if the container has it, but it doesn't. I can't seem to find its signature. Let's see this. There it is. Again, this is one of those things that I have to. If I can't find it if you cannot find it in the public symbol API, but it's documented in the documentation, that means it just was not exposed, and you should be okay to actually go and use it. That's kind of the rule I've been following. But if they tell you otherwise and they suddenly delete it, that's something that we need to. I would throw my hands up and just say, okay, you can't do that because it's a part of the public API that you publish online. So has initial element p. What it does is it takes our object and it looks internally into that value that we just saw here. This guy, this flag, and this is all it does, and it checks to see if there are initial elements. So that's something a little bit interesting. So although there are contents in here, the contents is not what you're looking at. You're actually looking at a flag that's built into this container. And a lot of these containers have this kind of flag of whether or not it's been initialized, or it has an initial element inside of it, or so forth. So another way of actually initializing this container, because I did initial contents, is actually, and let's go ahead and reset this. This is one way of adding values into this container. And again, what I'm showing you here is just with A-list, but it works with a lot of other other data structures that are built in here. Like, just to give you guys a quick review of what's actually available, there's things like DAGs, red-black trees are available, sparse arrays are available. I saw some inside there that they also have a quad tree implementation for those of you who are writing like 2D games, which might be useful. You can also use quad trees for other things, but that's the most immediate thing that came to my mind. There's also library access things for, say, they have an array wrapper, a vector wrapper, which is slightly different than arrays for fixed size arrays, my understanding. And then you have also something for for multi-dimensional arrays, like and vectors is more like, I think, a C++ vector still, based on looking at their API. There's also doubly linked lists as well inside of it, and as we will soon see, there's also something, and this is something that I want to play around on in today's discussion, which is the ring buffer, which gives you kind of a circular list for you to do things like if you wanted a fixed size buffer for scheduling. Usually you'd want to use a ring buffer, because then that way you can always rotate and you don't necessarily accidentally incur another cons just because of the dynamicity of a lot of the built-in insertion functions in Common Lisp. Let's get back to associative lists here, which another way of actually being able to insert values is something called Initialize Container. So let's look at, I hope this is, nope, doesn't look like it's available here. So Initialize Container. Initialize Container basically takes in a a list, and all it does is it kind of like, it doesn't actually like change it. That's weird. Well, give me a second here. Thought I reset this guy. Okay. And then let's see this. All this guy is doing is, and this initialize container is doing, is kind of the same thing as what make container does, and that is it resets the flag, but it doesn't actually provide any sort of contents inside of it. And this is something that you may need just in the case of, if you ever needed to go and either reset a container or say, just making sure that something is not nil. I think make container internally uses initialize container, which is why it's a internal function. But a lot of these functions, for some reason, some of them inside of the documentation that I followed the last couple of days when I was looking at this library. Some of them are available that are part of the public API. Some of them are not available, but are still there. So they're not intended to be used for public consumption, but it's still part of documentation. I'm trying to kind of filter out some of those things as I've been going along, just so that I can give you kind of a good indication as what the core API is available or not. Okay, so we talked about insertion and associated lists. We talked about how to construct them. What APIs are there for, filtering and so forth? Well, there is, for example, I think this is something that I can use because it deals with key value pairs. There is predicate functions like every key value p. This guy takes in a container, and it will take in a predicate, and here I'm just going to write dumb predicate, saying that, let's say it takes a lambda, it takes a key and a value, and it returns, and type p of key is of string, and type p of value is integer. Alright. So let's see what happens when we run this guy in the REPL. So you can see here what we're doing is you can use this for type checking, runtime type checking, pre-list, just to make sure that your key value pairs are in your associative list are all of the same key and value, and you could throw up errors if not. So like if you say that this is, for example, a single float, you will get warning, undefined single float epsilon. Okay, that's interesting. Oh, that's right, because they're all there. Since all these are integers and fixed them, they'll fit in the same hierarchy. So let's also say, let's try something that will give you nil. Let's say that these are both strings. That's weird. That looks like a bug. So I didn't encounter this when I was playing around with it, but I didn't actually try this type system kind of stuff just to bring in what we were doing last week. So this is something that I'm going to have to go and investigate a little bit more. I'm just going to write this down as a note. Give me just 1 second. Is it called? All right. Let's move on. You also have, if you want to print the container, we have CL containers, print container, and this is just going to really just print out the container object, but it does not, since our test list doesn't have anything in it, you won't see anything. So let's go ahead and add some contents to it and print it. You can see that what it did is it's actually printing the values. It's not actually printing the keys. That was a little weird to me, but I guess that works. And it's putting them in reverse order because that's how the contents was actually inserted into it. If you actually look at the contents directory, it was inserted in reverse order. All right. So let's move on to a different container from A-list just for a moment, because A-list there's a couple of things on the key value front that it looks like I still have to go and actually check out just to see if I understand what the API is asking for. So I'm just going to table that just for a second. And I'm going to move on to a different data structure that I was playing around, which was creating a vector. Now, like I mentioned, there's two types of vectors inside technically there's three types, but fixed size vector is basically the array. So I'm just going to ignore that for a moment, calling that a vector, but it is technically, for all intents and purposes, a fixed size array. So we have our text vector, and we have two types of vector containers inside of the CL containers library. The first one is make containers, CL containers. No, I'm just going to use vector container for now. And here, I'm going to go ahead and see if I can get this to work, because this is assuming I can actually do this, right? No, can't even do it there. So it looks like there's a problem inside the make container because it doesn't actually do what it's supposed to be doing, and making sure that you can actually access those arguments and insert them inside the underlying data structure. So this is, there we go. So now if we look at the test vector container, you'll see unlike the associative containers, which is equal, this one uses not EQL, but it uses EQ for its testing type, which threw me off a little bit, just because, again, like I said, I'm not entirely sure why each of them have to have necessarily a different default for it. I guess that there's a reason for it, just because of either since I didn't specify the element type and so forth on it, that might be the case. But let's see. Actually, let's try this. In the case of this guy, let's say element type integer. Let's see what happens when I do that. Okay. That's why I couldn't get this working. This is exactly like make instance. This is what I forgot about this. Okay. So I take that back about there being an issue. It's just that it didn't say init args, and it was just saying args. So what this is doing here is, if we just take this example and we print this guy out, you'll see that each of these constructors are going to require you to know what the underlying direct slots are available to you. Now, you're going to have to go and look into the documentation for this, but so for example here, I could have written contents. Let's try A dot 1 B dot 2. Let's go ahead and says has initial element P is true, and let's see what happens when I do that. Interesting. So it did not actually do what I expected it to do. Maybe it's because I did has initial elements instead of just keeping it at contents. Do that. See what happens. Let me see one more thing. If I do the original associative break, this guy, A1, 2. Weird. So for associative containers, it looks like there is some problems with the constructor. It might be because I'm using the wrong container constructor. Let me just do one thing here. Let's see, colon, make node for container generator. Yeah, it looks like this should work, but it does not work as intended. Okay, so that's the issue. All right, I'm gonna go ahead and put up this example up and check to see if what the author says about this after we're done. I'll look at their GitHub repository. Okay, so let's continue on our discussion on test vector. Test vector allows you to specify a couple of things to make container: the element type, the contents. Let's say that our contents is a vector of 1, 2, 3, 4, 5. And for folks who are just joining us and are wondering what this is just the reader macro for creating a vector array. So if we do that, and we look at, clear this up so that we can actually concentrate on test vector. Interesting. It looks like contents cannot be set up inside of it, even though I could specify the element type. Let's see. Let me just do one more thing. Let me see if I could change the test function to equal. Okay. And nice. Okay. So there's a weird thing about the contents for some reason that you cannot change when you're making a container. But you could specify everything else. So I wonder if that's the same thing here. Let's see if this can happen. As initial element P is true. Let me just pull up the slots here so I can have them at my disposal. The initial element, let's say, is 1, and let's call our test EQ. Let's see what happens here. There we go. So you can see here what this is doing is it allows us to actually construct the container, but it doesn't allow us to actually pass in any initial contents into the container, just because. So I just learned something here live. So that is, if you want to set up your container for initial construction, but you want to add initial contents to it, you have to do it in 2 steps. One, you need to specify what test methods and all this. This is all for validation. You need to make sure that if you're adding an element and it doesn't have one, it gets an initial element. If you're adding an element that matches the test method that you provided into it, it gets all validated at runtime so that it can throw the appropriate error. But it doesn't look like content itself can be accessed at the initial construction, just mainly because it doesn't look like it's doing like a make instance and doing a set internally. That container object method may not be constructing the object in a way where you can actually specify initial contents into the initial constructor. So you would end up having to use separately, as a result of this, what we saw earlier, which is add initial contents. All right. So once you do this, I'm sure this is going to throw up an error. No, it didn't. Weird. What does this do now? Okay, I guess this is, so I'm going to figure out an example on this and see what it is doing in order for it to use this initial element test function. Okay, so sorry if I'm jumping around, folks, just because there's a couple of weird things about this when I played around with it before that I'm just catching up on, and I'm now just experimenting. So let's get back to test vector. So we created something with test vector. We're going to go ahead and we have our elements here. We could go ahead and now do CL container. Go back to this. Go to this. Okay. And do initialize, add initial contents into test vector. This could happen here. It doesn't look like it's available. Okay. Let's see here. Initial contents. Let's do 1, 2, 3, 4, 5. Let's see. There's no. Okay. Then I'm using the wrong one here. So what do I use? Insert item, I guess. Yeah, I have to use insert item because vector container is basic vector container, which is the vector container mixin. And the vector container mixin contains contents as array, right, type container, and so forth. So what is the insertion method for this? Let's try insert sequence just to see if I can do this. Vector 1, 2, 3, 4, 5. Let's see here. Looks like that works. So we can use insert vector. Insert sequence actually works. So insert sequence allows you to add initial things. You can also do insert item, which allows you to also do insert item. Pass in test vector, 6. Let's do that. And if we go look at this guy and do a refresh, you can see that the elements are here. Now, the main thing to recognize is the fact that, again, I changed the equality operator. I changed and it is internally an array. Well, technically, it's a vector object, a Lisp vector. But if we try to add, so this will come in handy when we try to insert item. Let's try this. Let's say that we're trying to add a character here. That's wrong. That's weird. So there is something to be careful about. It's going to now have obviously the character h here, even though we said the element type is of integer. So it looks like although the element type and test values are there, it's not being used for validation in terms of the actual insertion of different functions. So that's something to be aware of. It looks like there's some checking that you need to do as well in order to use this. So it looks like it's a much more lower level library. But let me go ahead and delete that item just so that we don't get into any sort of issues. Let's see here. What's the best way to do this? Okay, so to do that, if we want to delete items, you could just do delete, delete item, and you see delete actually has several overloads. So delete item if, after, before. We're going to use delete item since we have a indexed container. You can just simply use delete item at, and as most of you are familiar with in Common Lisp, we are 0 indexed, so this should be the 6th element. So we removed the last item, and you got their items. A couple of other convenient functions that I'm just going to show through here, and then I'm just going to post this inside the script later on, is count elements. Count elements will give you, oops, sorry, clear, no, this, and hold on. Count element is not what I need. I need these count items is what I was looking for, not count elements. Count items. Count items. Wait a second. Count. Okay, count elements basically takes in a container. And let's say an item that you're looking at, let's say 2 in this case, and it has some default test values and identity values that you can go look at. In this case, since this container doesn't have a key, this is just going, that last value is going to be ignored. You can see that it's going to count the number of elements inside it that equals that. It also has a size structure, I think. Yeah, it also has a size, which is what I was thinking count elements, but I forgot it. They match the C++ container. This size is kind of like length in Common Lisp, and I'm almost certain that in this particular case, this is actually using length inside the stream, internally inside the library. There's also you saw in count elements also that there's 2 specific ones that we saw there. One was count elements and count elements if. Count elements if is kind of an additional thing that allows you to pass in a predicate instead of a value. So before we passed a specific value, and it'll go iterate through the list and check all the values. But let's say that we wanted to see how many elements are integers. So we can just go ahead and pass in a predicate here, like predicate P, and it'll tell you, the same thing that we can actually go ahead and use. The main thing to take away from this is at least in the API realm, a lot of the API functions are very, very, very uniform and are similar actually to the Common Lisp stuff, but also I think the author came from other languages where size is used to check the size of a container instead of length, things like this. So there is a couple of differences in terms of the naming schemes in terms of the API naming, which shouldn't be a big deal for folks who are getting into this library, but it is something to be aware of. A couple of other things that I'm just going to show off here is we saw with count elements that you can also do things. You can also have, you can essentially filter through, and which is one filter method to actually check to see if something is countable. You can also search for elements. So here there are many searching functions. You have to pick the right function that matches the mix and representation of the actual object to not be. So in this one, for example, search for node will not necessarily work for test vector because vector is not a node-based structure. Also, search for node star won't necessarily work. Search for matching node also will not work. Search for key will only work for associative containers. These are things that I'm just mentioning to you that there is a different search function for each one, mainly because of the fact that given the characteristics of the search, you might want to be aware of what type of search you're actually doing. So in this particular case, they went ahead and instead of creating a single search, like a generic algorithm search, that you can actually go through and figure out what is the underlying iteration strategy. They made a separate function for each type. So this is a little bit what was the term that was being used? This is a monomorphism for folks who are coming from the Haskell world. Essentially, they're using a function for each specific type of class that's available. For our cases, we're going to just use search for item. Search for item takes in the container. Again, takes in the value, and it will return the actual value if it exists. If it does not exist, it will just return nil. Okay. This is another thing that I'm just going to bring up that's a little bit of an annoyance just compared to some of the other data structure libraries I'm looking at recently. Although the API is uniform, the return values aren't necessarily uniform. And what I mean by that is all the search functions, instead of providing, say, multiple return values, that gives you the value and whether or not it's been found, which is commonly used in hash table searches. If you look at get hash, for example, inside of Common Lisp. Here, the containers determine the return value for the APIs that they're going to be using. So if it's a built-in container and it's built-in container searches, and I'm specifically reducing myself to containers that were wrapped so that it follows the same API that CL Containers provides. In that case, you have to look at what the built-in container is in order to know what its return value is. And some of the documentation does tell you the return values specifically, but other ones, they say it's based on the data structure. I can't really say much more about that, but I'm giving you a warning about it just because I was burned by it before too. So let me see here. I talked about searching, I talked about size, I talked about counting. we cannot leave this discussion without talking about map and reduce, because obviously we're in Common Lisp. Common Lisp has one of its greatest features is the ability to be able to transform functions and create new elements. We have to talk about that. So in the case of I'll talk about reduce first, and then I'll get to map, because let's see here. Yeah, let's talk about reduce first, and then I'll get to map. Reduce elements. So there's reduce elements, reduce containers, and reduce key value. Again, this is very much in conjunction with this monomorphism. So all node-based data structures will have a different reduction method than all things that are in contiguous-based structures and so forth. Now, I thought at some point that I could use just reduce container, but I've noticed that reduce nodes and reduce elements, reduce key value each have different signatures, and I didn't quite see in the reduce container, in this reduce container top level function, it determining which one to actually dispatch on. So so far I've been using reduce elements just because I've been dealing mainly with vectors when I've been to investigate vectors. And this is a pretty straightforward signature. It's very much like reduce right now that we see in Common Lisp already. So it's a direct map almost. And this will take in our container, the function that we're actually going to be reducing on. And since our initial value is already at 0, our start is already at 0, I'm not going to actually have to those are the start and end indexes. I'm going to go ahead and say our initial value is at 0. You'll see that we can actually go in and we'll end up doing a standard reduction here. Behind the scenes, again, I'm almost certain that this function here will use the built-in reduce to actually go and implement how it's doing its reduction. Now, while I have you, I'm just going to go ahead and try reduce container, just because when I looked at this before, I wasn't sure if this would work, but we will see. This should do the same thing that we saw earlier. Again, start and end inside of the signature is all about the indexes into the container itself. I'm going to specify this, and we'll see that we get 21, which matches because CL content containers, contents of the container, that's the vector. As you can see, it's 1, 2, 3, 4, 5, 6, and if you add those up, you will see that it will become 21. Let's see here now. There are other, common things that we're all kind of, familiar with. For example, reversing a container. When you reverse a container, it is a destructive reverse. So if we go ahead and call the contents on our vector, it should be the other way around. A lot of these, and this is something that I'm going to try and reiterate. I've been trying to reiterate throughout this presentation on this library, and that is, this library does not care about immutability. It is a stateful thing. Mutability is part of its design. It is intentional. And you get certain optimizations for free by doing mutability in some cases. I'm not encouraging you to use this library if you need it to have more of a persistent data structure. There are other libraries that you could use. Again, Sycamore and FSET certainly will be good basis for creating your own persistent data structures. But keep that in mind when you're using this, wondering why there aren't any versions. But that said, I'm going to mention also that given the fact that this is based on a mixin architecture, and these mixins are available at your disposal, you could certainly use the abstract container base class to create immutable versions of these data structures if you really need to. All right, it's just that what's provided built in does not provide you those that functionality and that support. Let's see. Oh, let's talk about one more thing. For those of you who are from libraries like, say, C++, coming from languages like C++, sorry, and even Python, you might be wondering if this library provides some standard, algorithms at your disposal. We saw a couple of them already in the case of reverse search, count, and count elements if, count elements after and before, and so forth. In addition to that, there's also a couple of functions related to uniqueness. So there's unique, and unique is particularly useful to, especially if you're using this in certain situations where you need to filter out and only do transformations on unique elements, or you're trying to figure out how many unique results something is and so forth. This already provides you the ability to be able to grab some of this. Now, to really drive this home, let me go ahead and create a new vector. Actually, let's see if I can just do this. Actually, I don't need to do that. Let's go ahead and do this. Yep, that a couple of times. Then add this. So now, if we go and look at the contents, this, we see this many, insertions of duplicate information. If we end up calling unique elements, obviously it's going to return a list of all the unique elements inside of the list. So you could see that it's going to go ahead and just do the standard reduction. But this is a immutable operation in that if you go in and call, contents, the contents were never changed. Unique elements does not actually destroy your container. Some of these functions do the destruction because you've asked it to. So reverse, for example, is essentially n reverse inside Common Lisp. It does not guarantee that it's not going to be modifying your container or not. So please look at the documentation and look at the return values so you don't accidentally get burned by that. We also have some algorithms for removal. Again, these are destructive algorithms. Let's say that we do this container, and let's go ahead and remove all the even elements. You can see that when it returns the instance is basically indicating to you that I modified the container, and I'm returning you only what is. You can now access the contents of the container to see that it's been modified. If it does something like this, and this is a nice user-facing feature for folks playing around with it in the REPL. If it's providing you a return value that is distinct, that's more than likely meaning that your container was not modified. But if it provides you essentially this, which is the instance that you are currently dealing with, and you could check that, especially given the fact that you bounded it to, in this case, to a def parameter. That usually means that the state has changed, and you need to go and check the contents to make sure that nothing else is screwy with it. One more reduction function that I wanted to show off, and this is similar across containers, but I'm just going to show it off in terms of vector, is collect. And then I'm going to just end this with a couple of mentions of some of the direct methods which I haven't actually talked about yet. CL containers provides essentially this collecting item, which is another type of reduction. So in here, you have a couple things that allows you to essentially construct either elements or collect elements. Collect elements basically, and I think that this would be best addressed with an example. I would say, based on my reading of the documentation, my understanding of it is that it essentially is like a map followed by a filter. But let's try it. Let's just see what happens. Because I just found this morning before the presentation. I was like, huh, this looks interesting. Let's go and check it out live. So first, we're going to go ahead and reset our guy. I'm going to go and make this initial sequence a little larger. So let me just go ahead and do this. For I from 1 to 20 collecting. Okay, so we now have our sequence with the first 20 integers. What we're going to do is we're going to double it, and we're going to get all the evens. All right. So what does that mean? So we do this. Let me take this guy out. Example of collect elements. All right. So what we'll do is we'll call collect elements that takes our container test vector. We need to provide a transform function and a filter function. So our transform function is a lambda that takes an x and just simply doubles it. All right, cool. Our filter function, I'm going to go ahead and actually do this just to make it a little clear, is going to be essentially nothing more than even p, right? So now, what happens when you run this? 530y, and print this here. You can see this does exactly what we asked it to do. We asked it to essentially grab all the even numbers. Since we, honestly, since we doubled everything, everything is technically going to be an even number here. So let's go ahead and simplify this a little bit. Let's see here. Oh, okay. So what this is doing is a little bit different than what I understood. This is actually not doing everything's even number. This is first taking the filter first and then mapping to it. So let's do identity here just to make it so that we're seeing what we're doing. Okay. If we take identity, you can see that it's grabbing every element that's in here, all right, and doubling it. Okay, and this is pretty obvious. This is just 1 to 20 multiplied by 2. Okay, this is the first 20 evens. If we provide something other than identity that we saw here with even, what it's going to do is it's first going to filter the container, grab all the even numbers, and then transform them, right? So let's change this a little bit by saying that we're going to, instead of doing doubles, let's go ahead and increment all the even numbers by 1, okay? This should really kind of illustrate it. So, this is going to be 2, 2 plus 1 is 3, 4 plus 1 is 5, 6 plus 1 is 7, and so on. Right? This is somewhat useful if you're trying to do transformations on top of particular complex predicates, which I thought was pretty neat. But again, like I said, my understanding of the function originally and what it is actually is two different things. There's another one that I think I should mention that is kind of in the same light, and that is collect elements stably. This is a stable collection in that it tries to it's kind of like stable partition in C++ in that it tries to make sure that it just try and see what the best way to describe this is. It rearranges things in such a way that that the predicate, that all the elements for which the predicate returns true precedes all the elements for it to return false. So, unlike partition, unlike collect elements, that is in this library's case, the order is not the order is actually preserved. So that means these aren't reconstructed and thrown on the heap in different memory locations. They're actual locations and are stayed the same, and it keeps an internal tracker behind the scenes to knowing what was filtered and what was not filtered when it does this. So keep that in mind. This might be a little faster in some cases than collect elements. What was the other one that I wanted to look at? The other one that you could probably use also is collect items, and that's more, again, more of the same. You do see, though, that all the things are first about filtering the data to make a smaller subset and then transforming the information. Now, some of these collect things that you might be seeing here in there, for example, like collect using map and filter. This one is particularly just allowing you to provide a map function and filter function that you can, well, let's just go ahead and try it. So let's go ahead and do what we were doing before, increment fx. Let's say our filter is going to be essentially even p, and the rest of the arguments is going to be just some arguments. So you could see invalid arguments. Huh, interesting. So this means that args must be, let's do that. Invalid number of arguments 2. Interesting. Okay, I need to go and look into this slide, this particular function. This one I didn't. This looked like, my understanding of it was that it's going to be that it constructs a new data structure from this collecting map and reduce that you provided, variadic arguments to. And it looks like if you look at the signature, that's what it's doing. But apparently the signature does not tell me the whole story. So I have to go look into what exactly the particulars are on this function signature, and then I'll give you guys an update next week when we continue on this. Before I end today, I just wanted to briefly mention, at least with respect to vector and even with respect to A-list, since these are the two main ones that we covered today in this library, in that on top of all the methods that I showed you that are part of the uniform API, there are a couple of methods that are specific to the classes in question, the containers in question. So, for example, given the fact that test vector is a random access container, there's a couple of things that are available for you, being that it specifically, using CL containers terminology, it implements the what's going to call it, the contents has arrays mixin, if I recall is the correct thing. And what it provides you is a couple of things that you can have access to using indexes. We used one of them earlier with relation to reduce, but there's a couple of other ones that I'm just going to briefly mention here. One is obviously item at, which takes in a vector. You know, it looks like it's not the contents has array mixin. It's because it's an indexed array mixin that that this works. And let's say that we provide this. You can see that we can actually access everything in the container at some random index. Additionally, it also returns. It also has CL containers nth element, which takes in a container and an index. And what the difference between nth element and item at is depending upon the indexed container, insertion order isn't necessarily guaranteed. All right. If we randomized, for example, the container insertion, you may get completely different results in one item at versus the other one. All right. Now, the importance about this is there's destructive versions of some of these functions. Specifically, itemnet has this version that I'll just show you here. Itemnet bang, all right, which looks like you can actually, in some of the indexes cases, but it doesn't look like it works in this particular case. It modifies the item specifies by the indexes to a specific value. So let's look at this container. Let's say that we want to modify the first element and say that it is 3. All right. So what you did here is let's look at the signature. You have the actual container that you're trying to modify. You have the value you want to insert or connect to, and you're specifying the index at the end to what the value is. This is a little different than what we saw before when we were looking at Sycamore, where the arguments were flipped. The indexes were first, and then you went ahead and actually modified based on the value that was at the end of the arguments. Little change in API, but if you're using one versus the other, you'll get used to some of these changes, right? Now that we've done this, okay, if we go and look at the contents of the vector, you'll see that the first element has been changed to 3. All right. This is something to be aware of, that you don't necessarily need to use, and I guess this is something that I'm bringing up because of what Common Lisp provides and what this API has done in terms of breaking some usability. Most people who deal with data structures in Common Lisp, okay, again, list, associative list, arrays, hash tables, what have you. Most people are familiar with a generalized expander or setf expander for setting values to a specific data structure. In this library for indexed containers you just saw, you don't do that. you don't use a setf expander and expect that item@, can return the cons cell to which you can actually then call setf on to modify. What I mean by that is you can't do something like this, as far as I can tell. Tail containers item@, test vector 0, and then say 3. This is something I've not actually tried out and tested, but my understanding of the API, this is not possible. So I'm just going to let you know about this. If folks tell me you're wrong, I will certainly correct myself on this, but this is just my understanding of this. This will not work. Let's see. This should not work. Does it now? Damn. So why the hell do they have the other one? Is it just a convenience? Alright. This is idiomatic Common Lisp. Alright. Using a setf expander. I don't know why you would want to run away from it, so I'm glad that this isn't the case. But my understanding of the item@, thing was that they're expecting you to use the item@ bang when you're actually modifying containers. This is non-idiomatic modification of a container. And this is, I'm just going to pull this guy up here and paste it. Alright. This, most people will be familiar with. This is very API specific. A couple of other things that I wanted to mention is, what was it? I think CL container. There's also CL container, first element, test vector. Okay, and then obviously when there's a first, there's a last. Tell you what the last element is. There's also set first and set last for some reason as well that you can also use if you really wanted to use it. Set. What is it? Oh, it doesn't look like this actually exists anymore. Fantastic. That's good. That's good. Looks like this API is a little outdated from what is originally there. Okay, cool. I'm looking at a couple of methods that are mentioned in the documentation, but don't look like they've actually been set. So that's good news. Just looking at my notes. Let's see here. Okay, I think that's it for today. I wanted to cover. Again, this library is fairly huge in terms of the number of mixins and number of containers. There's about 7 or 8 different objects, but I hope I gave you a fairly decent overview of what the library provides, as well as some of the, as you clearly saw during my demonstration, some of the clear roadblocks with what is actually available in the documentation and what is not, what is actually being thrown out by the REPL that's available by the library in Quick Lisp. So if you guys want to experiment with this library, again, you can get this from Quick Lisp directly. And next week, I will touch base on just maybe a couple of errata from today's presentation, but I will continue our data structures exploration with really a library that I'm looking forward to, but it's a pretty big library that I've been slowly reading through the documentation, trying to get some really solid examples in, and that is the Lisp interface library. So that is next week. I hope you all have a good afternoon or good evening, depending upon where you are, and I'll see you guys next week. Thanks.